Okay, good day everyone. We'll start with another algorithm today, which is basically an extension of the previous algorithm that we studied, right? We studied about DDPG, deep deterministic policy gradients, right? We had two actors, two critiques in it. The main actor, main critique, the target actor, target critique, right? That was done to balance the learning, stabilize the learning rather, right? However, with a single critique, one of the issues that, okay, the actor update or the one that is responsible for the policy itself is through the gradient of the critique, right? So the estimation or the values that the critique gives significantly impacts the actor, which in turn affects your policy, right? So the better your estimation, the better your policy will be, right? So what happens in DDPG with a single critique, single main critique and single main target is that these updates are at times overstated, okay? In the sense that they will probably give a very high value for a certain action when it didn't deserve that, okay? Because remember, this value computation is through bootstrapping, right? Which is an estimation. So there might be an error in that estimation path. So how do we overcome this? In order to overcome this, we came up with this algorithm called twin deep deterministic policy gradient, TD3, right? Twin delayed deep deterministic policy gradient. Yes, so like I stated, one of the significant issues that we might face with DDPG is overestimation of the Q value, right? Which would then propagate to the actor, which would then in turn give you a not so good policy, right? So your RL agent training will not be very effective. In 2018, an improvement on DDPG was introduced, okay? Not only overestimation bias, but even okay, what does the critique does? Critique gives the Y values, right? Which is the target Q value that you have, and the Q updates its parameters based on that target Q values, right? Which would in turn, the gradient is propagated to the actor, right? Now this becomes very noisy. Despite having a main and target critique, despite these two, the reward functions or the Q functions rather will become very noisy, right? Which would in turn mean the actor's policy being very noisy, right? So remember, there was a line in the previous lecture which stated that what this entire actor critique paradigm does is it will try to judge or gauge the sensitivity of the action, right? So what critique does is critique makes a plane, a very, well, preferably a neat plane, right, without any random spikes, okay, and the actor will try to go along that surface, okay. It can be a hyperdimensional surface, not a 2D or 3D surface, because of the number of states and actions you have involved, okay. So now what happens is, when we are trying to gauge the sensitivity, so we see that how much changing a actor slightly, right, the parameters of the actor slightly affect the value function, right? And remember how we introduced noise there in DDPG? The noise was introduced after the action was generated by the actor neural network, right? Just before it goes to the neural network, right? So there was no mechanism of feedback of this noise to the critique, right? The mechanism was only through the states and rewards it was getting, right? But we didn't exactly know what action was being played or executed in the environment itself, right? That is after the addition of the noise parameter, right? And why was the noise added, by the way, in the first place? To encourage exploration, right? So now you will see in TD3 that we try to address these issues, okay? So yes, now here you have two critiques, okay? In the sense you have earlier also you had two critiques, but one was main, one was target, right? Here in target you'll have two critiques. So basically 3 neural networks in every set, okay? Actor, critique 1, critique 2. Actor, critique 1, critique 2. Got it? Clear? Okay. Now why do we have these two critiques, Q1 and Q2? Because each of them will have the same input, Q1, Q2. Okay. No, they have critiques, right? They are critiques which gives you Q1, Q2. So you have C1, C2, which gives Q1, Q2. Okay, right? Now the input to the critique is states and actions. Actions coming from actor A1. Well, you'll have one actor. You'll have only one actor, and this will again give this thing. Plus the environment here will give states here and states here as well, right? Now both of them are getting same inputs, right? But the values that you will be getting, Q1, Q2, will be different. Why? If the inputs are same, the outputs are different, what does it mean of this? Say this is a block. Exactly, the block itself is different, right? Because of the initialization that we have here for the two neural networks will be slightly different.
So they're not identical.
They are not identical. So when they are not identical, despite taking in the same inputs, the output they will give will be slightly different. It can be same, but it can be different as well, right? So when we get these two Q values, okay, what was the main issue we were facing in DDPG? Overestimation bias, right? So now in order to overcome the overestimation bias, you got two values. What do? Sorry? Smaller one, exactly. So you choose, your Q will be the minimum of the two Qs you have, right? Clear? Why the minimum? That way you counter the overestimation bias. What is overestimation bias? It's basically an error or an issue that the critique network is predicting the Q value for that particular state action pair to be higher than what it actually is, or than what it actually is supposed to be. Why does it even do that in the first place? Because Q value is the reward plus some bootstrapping term. Okay, this is an actual term, this is not an estimate. However, this is an estimation, right? This is an estimation. So this estimation can be prone to errors. And in fact it is, right? Because of this term, the predicted Q value will be higher than the actual Q value. Clear? So now when you have two, the likelihood of both of them having that overestimation bias will be very low. Right? So in that case, when you choose the minimum of the two Qs, okay, you will compensate for the overestimation bias, right? Because what the critique is trying to do, it is trying to reduce a loss function. What is that loss function? Yes, the error. What between TD error, right? What is TD error? Q minus YT, right? Which is a moving average, moving target here, right? Which we assume, or at that point in state, we think that this is the stationary target Q value that we want to reach, right? Yes?
But what is the difference between the structure of frequency?
Sorry?
What is the difference in the structure? Like, how they differ in evaluating or minimizing the function?
Okay. So say you have two neural networks here. Both of the same size, exactly same activation functions, everything structurally both of them are same. However, when the initializations are different, the weight initialization, weight and bias initializations are different. Say you have 0.01, 0.5 for one, and the other one 0 and say 0.9. Even when you give same inputs, a bias of say 0.3, here you have a bias of 0.7. Okay. Now say the input is 1.2 and 1.3. This will be the same for both systems.
Output will be different.
Output will be different, right?
This depends on like
Initialization.
Both of them will be converging at the end, but at the beginning we want to get the minimum as low as we can to minimize the difference between the expected and the actual Q.
No, again?
I mean, usually, here the weight changes or not? The weight changes update.
Yes, yes,
right?
that's the learning process.
Both of them should at the end update into the same conversion to the same weight source, right?
Okay, right, okay. Yes, okay. For that, so now we have two blocks, target block and the main block, right? In this you will have in this you'll have three, okay? You'll have C1, C2, A1, A1, C1, okay? This is basically what you will be taking out after, well, only this basically, you just need this, right? At the time of deployment, it's only the actor that is deployed. You do not have, even if you train a critique, you don't take it and deploy it on a real hardware. Why?
Because trying to minimize maximize the expected return.
So you want, even in a real hardware, to increase the expected return. So why don't you deploy critique on a real hardware?
It would be continuous learning and adjusting, so the performance is unstable.
The output
No.
is not related to the policy.
Exactly. The output of critique is something called a Q value or V, right? Which has nothing to do with the physical actuation of the system. The physical actuation is done by actions, which is generated by the policy, which is generated by the actor, right? That's why you only take the actor, okay? Okay, yes, coming back to that question. So now you have two critiques, okay? What they do is they give two different Q values for TD error calculation to this C1, right? Now this C1, the main C1, while updating its parameters, it will make sure that it selects the lower value of these two. Okay, we have C1, C2 in the target block and C1 in the main block, which is critique. Yes, so that way when you choose the lower of the two values, you do not see abrupt spikes in the Q value surface. Assume your Q value to be a continuum, okay? A surface, a 3D surface, right? So if you choose the lower values always, it doesn't mean that you are not always getting you're not trying to maximize the returns. No, you're not doing that. It is just that during learning process or during the training process, what you're trying to do is you're making sure that this surface, because it corresponds to a physical system, for physical systems, like I told earlier as well, when you change the input by say 2%, your output shouldn't change by a lot, right? It shouldn't be, at least it shouldn't be drastically opposite. Like say if you increase the volume control in your cars, maybe for example, if you increase it a little bit, say by 2 points, it shouldn't blast the windows of your car, right? It should still be audible, but it should change slightly. Why? Because there is continuity. Okay, I forgot to mention this in the previous class. That is the reason why we use OU noise and not Gaussian noise. We do use Gaussian noise, but OU noise is preferred when we inject the action that is generated by the actor in DDPG. Why? Because OU noise, it is pronounced as Ornstein-Ulbach. I'm assuming, yes, okay, it's quite complicated. So yes, OU noise, in this regard, what it does is it will see to it that there is some continuity in the noise that is injected, right? It is random noise, but it has some kind of correlation. So that way it is more applicable for physical systems.
So instead of Gaussian, I don't know what is OU, but from what I understood, it's more like continuous or gradual noise.
Yes, yes, as compared to so exactly. So now coming back to this point, so here also you want to make sure that there is no sudden changes in the Q value function, right? So that surface is smoother. That is the reason why you choose the minimum of the two values. Yes.
Please, I can't read the video handwriting. Explain that.
Okay. So you remember we have two sets of neural networks, the target and the mean, right? and the other one, the main, let's say the main neural networks, right? So the target networks here in TD3 will not be 2 neural networks, it will be 3 neural networks.
I'm sorry, but could you remind me what target network is?
Okay. So target networks is something that is you have to stabilize the training so that the changes don't happen drastically, right? Otherwise, say during the training process, because of the feedback that we get, okay, say in one episode, you get a feedback that states that, okay, fine, this action is good, this state is good. So that way what you will try to do based on the actor critique paradigm, you will try to increase the probability of that action significantly, and at the same time, because of the critique part, what you will try to do is you will give that state action a higher value. So you will increase that number as well, right? Clear? However, when training, say in the very next episode, what happens is the state just adjusts into it, or maybe even the same state, but the action value goes down significantly, right? So now you'll have to suddenly decrease all the weights. This will destabilize the training. So in order to compensate for this or limit this sudden changes in the weights of the training, we have 2 sets of neural networks, a target neural network and the other neural network, okay? Both will have 2 neural networks in DDPG, an actor and a critique. However, in TD3, you will have 3 networks, 1 actor, 2 critiques, okay? 2 critiques will both take the same input, will both give the same output, as in the quantity that they are giving. Both will give the Q value functions. However, they will differ numerically because of the initializations of these critique networks, the weights and biases. That way, when we are selecting for the minimization of the TD error, which also happens to be the loss function for the main critique network, right? We select the minimum of the 2 Q values. That is to ensure there is no sudden or abrupt changes in the Q network, plus there is no overestimation of any state action value function. Okay? So when we do this, we then get a continuum. Okay? Clear up until this point? Yes.
How we are setting up the initialization value of the 2 critiques here, C1, C2?
Random. Or there are some methods that you can follow, but they are not theoretical methods or the only way you can initialize. For example, say you're using Python, you simply use the random function and use the random values, that's it, right? So there is no rule as to how you are generating, how you are randomizing or initializing the weights of the critiques.
Doctor, again, the OU noise and the Gaussian noise thing, if you again tell that thing, I didn't understand it.
Okay. Gaussian noise will, in every instance, very randomly pick a random variable. Okay. However, with OU noise, when it picks a certain random value to inject with the action, in the second episode, it will try, or in the next iteration, it will try to pick a value which is related to the previous value. That way, you will have more continuation, right? Like say, suppose, sorry.
More stabilized.
No, it is nice. It is not stabilized, obviously, but it is correlated, right? You can read about it. Otherwise, I'll explain it probably in the next class in more detail. Okay? Yes.
Is the bootstrapping error cumulative or each iteration?
Cumulative in what sense?
In the sense that there is some error in
Okay.
the first iteration,
Okay.
and then in the second iteration, that error is added to the.
You tell me whether it's cumulative or not.
It should be cumulative.
How?
Because after first iteration, the gradient is sent back
Right.
to the actor,
Right.
and then so based on this, with this error,
Okay.
what the actor has learned,
Okay.
he will choose another action,
Okay.
and then that will influence the.
But when it chooses the next action in the next episode, again it will get a reward, which is a real value, not a bootstrapped value, right? So for that instance, yes, that bootstrapped error will cause fluctuations or probably spikes in your Q value function continuum. However, in the end, it is not. That is why DDPG is still used, because DDPG will not give you an incorrect policy. It is just that the training is not very stable, right? Okay. Yes.
See here that the update actor and target networks
Yes.
So over here, what do you mean like like what updates the actor? Is it the best of the minimum or the minimum of the two critics?
Okay, I'm coming to the actor update, but first I'll complete the critique part, okay? So when we are doing the critique updating, so till this point it's clear, right? For the loss function, we use the minimum of the two Q values. That way, remember there was a formula 1 minus this thing W plus, what was it? Yeah, it was plus something. So basically your updated weight will be, will have this term, right? Which is basically a soft update term, right? That way, what you're trying to do is you're not directly copying the say, okay, after this loss function updating, right, your critiques parameters changes, right, and you have the target network, okay. You're not directly copying the episodic parameters that you have to the target network, right. You do it in a soft manner. That is, whatever the previous value is, let that be, based on that previous value, change it just slightly from what update you're getting. That way your critique parameters will not change drastically, right. So when you are doing this, where was I? Yes, when you are doing this, so you have target networks there for that, right. So this target network update frequency is smaller, right, because the main one which is interacting, that will change at a rapid pace. However, the target networks will change at a smaller pace, okay. Now let me mind you something. You had actor which depends on the gradient of critique, right? Right? Now here you are getting two critique values. So which gradient should the actor take? We are taking minimum for the critique update, right? The minimum that you are choosing, the minimum function that you have is for this loss function which is responsible for critique, right, not actor. So now when you are updating the actor based on the gradient that you have, right, what value will you use? Q1, Q2, minimum of Q1, Q2, maximum of Q1, Q2, average of Q1, Q2. Okay. Any other answers? You said minimum, right? Why minimum?
Since it's the one that can give us the minimum variance in terms of.
Okay, but remember I told a term, or I told a sentence that we are not trying to reduce the reward that we are getting, right? We are just trying to stabilize the learning. That is, we are trying to get a continuum, a smoother surface of the Q value function, right? Anybody else had any answers? I'll come back to that. Minimum, average, maximum, or one of those two. Okay, why average? Okay, account both of them. But when we are doing critique, what are we doing? We are taking only one of these two. Minimum is also choosing one between one of those, right? Not two of those. When we are updating the actor, we choose only one of these, and that is not the minimum or maximum. It can be anything, but once you fix it, say you are selecting Q1 in the beginning, you always select Q1 for the entire training, for updating the actor. Why? Why?
Because the same Q value, like that use a state action here. That's
Right.
score.
Right?
So it should be the same Q that J, because it has the future action in it or the future value. So I think they somewhat depend on each other. So it should be
Yes.
the same loop.
Yes, that plus what happens is when you are selecting the gradient, okay, you are taking the derivative of that, right? If you take the mean of this, how will you get the derivative? They are neural networks, nonlinear neural networks. You cannot add them and then take the derivative of two nonlinear neural networks, right? So average is out of question now. Maximum? No, then you will be maximum will not work, right? Why? Because this is a bootstrapped error, so it might not be correct. If you tune your actor parameters to always follow the maximum estimated value, you might get a wrong policy, right? If you do minimum all the time, you will get a very conservative policy, right? So that's why you just stick to one of them. You follow that throughout for the sake of continuity, like you said, right? In that way, you will get an actor which is not over conservative, okay, right? Or which is not even possible, like say take the average or mean, right? So you select one of this neural networks, stick to it for the gradient, and you use that only for the entire training, right? You cannot switch between Q1 and Q2 mid training. Clear? Clear? Okay. So yes, you have two critiques. Okay, yes, then critique, it is, okay, yeah, this is another important thing. Now, okay, I talked about the addition of noise in DDPG after the actor takes the action. So you don't have any direct feedback of the noise added, right, or the uncertainty added in the action for the critique updates, right? However, in this method, you do take the action which is already infused with noise for updating the critique as well, right? So now you do have a feedback of the noise that you are taking. You don't need the feedback directly, but you simply need it for the purpose of knowing what action leads to what states, right? There the critique thinks that this actor, okay, in DDPG what the critique thinks is this action that I took, one time it took me to this state, the other it took me to this state, the other it took me to this state. It will think that there is uncertainty in the system itself, right? However, it is because of the noise injection that's happening that you're going to different states. Clear? But now in this case, yes, the actor knows exactly what action will lead to what state, right? Clear? And if there is stochasticity in the environment itself, when the training is done enough number of times, right, the critique learns that basically the average is set out. Okay, it basically understands the probability ratio of how many times the action will lead to a given state. Say 80% of the time it will go up, 10% of the times it will go left for the same action, that is, right? Clear? This will enable or help us in getting a smoother policy, right? So when you couple this minimization, minimal selection of the minimal value of the Q values plus this feedback, then you get a more smoother policy. Okay. However, note that again the exploration is done through some random variable externally forced into the system, right? This is not natural exploration, right? If we remove that term, there will be no exploration. Clear? There is no incentive for the RL agent to explore. Got it? Yes.
Is the noise random here?
The noise is, it's epsilon greedy. Remember epsilon greedy method that we had? So you do take random actions there. The addition is random basically because you have a base action, you are just adding some uncertainty to that action. Okay. Yes, we talked about this, which is inherit positive noise. Yes, okay. So that's why we use double Q learning idea. And now this is, okay, yes, again, when we are for TD error, we use the minimum of the Q values that we have. Okay, fewer oscillations, which I already talked about. Okay, so this is basically an overview of the algorithm that you have. Take the action with the exploration noise, okay, perturb the environment that you have, you will get this tuple, okay, the tuple we talked about most, state, action, reward, next state, okay, and for the critique update, you take this action, give it to your Q functions or your critique networks, choose the minimum of those two, and then you optimize it based on that. Clear? And for actor update, you use only one here, you see, Q1 only. And after all this, you will update your target networks with dashes here. So the main difference here is you have twin critiques, not one critique, right? Even there you had two critiques, but they were not twins, they were one and the other in different blocks basically. Now you have them together in one block, right? That's why the name twin delayed, okay? Plus, okay, why delayed? Because you update the target networks in a delayed manner, right? So that's why twin delayed. And deep deterministic policy gradient is because it was based on that algorithm, a direct extension of that. Clear?